use your hands guilty. We're not animals.
Parametric equations in context. And we want to just open with the following. Guys, in today's lesson we're going to encounter a couple examples that will involve projectile motion, so we want to have a conversation about that. And right away, all the examples today, there'll be some initial velocity on an object, say. And I want to make sure you're clear. If we want to say, I don't know, a rocket at with a certain speed at a certain angle, I think it goes without saying after our discussions with vectors recently that the velocity components are, of course, magnitude of the velocity, the speed, times the cosine of the angle, comma, magnitude times the sine of the angle. So I put this up here, and I hope it's no surprise, yes? So those are the components of the initial velocity if you, say, launch something at an angle. Okay, so not a huge surprise there. The velocity, the initial velocity, that is, can be broken into two pieces, a velocity vector that's in the x direction and a velocity in the y direction. I know that might seem a little weird to take one movement and talk about its velocity in the x and in the y direction separately. But we are allowed to do that. It shouldn't be too much of a stretch to understand if you have some projectile, say, that's moving through the air, that gravity, nor any other, well, and we'll assume no other acceleration is happening in the horizontal direction. So that means that if you start going in the x direction at 2 feet per second, that at all times we'll assume that you're going at 2 feet per second. Well, guess what that is? That's just linear, right? That's just this equation here. So in the x direction, you have very simple motion if you make this kind of assumption. It's just whatever the x velocity is initially, which we already established was here in red, times however much time you've been traveling in that direction, plus where you started. Now on the back, by the way, the two equations I'm about to put up here, this one being one of them, up here are the box in the bottom of the back page. I think I don't have the x0 there on that equation, because generally we will probably have that be 0, but it doesn't really matter. You can. Yeah. V0. So that means the initial velocity, right? So that makes sense because, like I said, if you're going at 2 feet per second, that's the red velocity in the x direction, say, and you're going for 10 seconds, then it makes sense to multiply those to see how far you've gone. That's all we're trying to say. It's just linear motion. The vertical motion is a little more interesting because we have the same stuff happening in the y direction. That is, we're going to have blue times t plus an initial height. But we also have this quadratic term that's going to be introduced due to the acceleration on Earth, which is this g negative 1/2 gt squared term. So that will change things, but the rest of it should look familiar. It's just basically what was happening in the x direction. So the only bonus here is this extra term up front, the quadratic term. And by g we mean on Earth 32 feet per second squared, or in meters 9.8 meters per second squared. So depending on the problem, depending on the units being used in the problem, those will be the numbers. And again, this is all appears in the box on the bottom of the your sheet. Do you agree that g equals this, right? You see that? You see it? And maybe on the front at the top, right? Together, this is there. All right, but that's the. Now we're just going to try and play around with some problems here. Yeah. Yeah, for people who haven't thought about acceleration maybe yet, let's think about this. That is a weird unit, right? So that means that every second that your velocity, so if you drop an object, say, 1 second later, its speed is 32 feet per second downward. A second after that, its speed is 64 feet per second, right? Its speed. You might be saying, you said 32 feet per second, and then 64 feet per second. That's its velocity at these moments. So now I have to ask the question, how is it accelerating? And I think you would agree with me. You'd have to say 32 feet per second. Every second, isn't that how fast it's picking up speed as it drops? Every second, its velocity is increasing by 32 feet per second. So a second later, a second after that would be whatever that is times 3, 96 feet per second, right? So that's literally 32 feet per second. Does that make sense? And if you do the math, you get converted per second squared. Good question. I think we're not maybe very used to using units of acceleration, so it's a fair question. And I could say more about it if that still doesn't make sense. But. Okay, let's try a few problems. The first problem here, we're going to limit, and in each of the first couple problems, we're only going to try and have motion happening in one of the two directions. So, for example, we've got a boy throwing a ball out the window. I think we should draw a picture. That's what I think we should do. We got some building. We got a boy with his hand out the window. He's throwing this. Do you see the? Do you see the boy? Okay, there's the side view of the boy. All right, you can't see him. He's inside the building. But you with me? He's got his hand outside. He's going to throw the ball straight up, and then of course it will reach some peak height, and then fall straight back down, and then hit the ground down here. Yeah? So let's come up with a parametric model that represents this situation. That is, give me an x of t and a y of t that models this. X of t is fixed. There's no motion if he really is doing this well. There is no motion in the horizontal direction. So let's pick your favorite number to be x. What's your favorite number? 8. 8. I like 8. Okay. Okay. You can choose a different number on your paper, whatever you like. But in the y direction, we will all agree on what we're going to say for the y direction. Really, by choosing x equals, say, 8, we're just kind of naming where we think our y-axis is for us in life, right? Are you 8 units from the y-axis? That's where this is happening. Okay. Or you can pick, it doesn't matter. All right, but in the y direction, we do have something interesting happening. So see if you can follow the equation that we were just talking about here in terms of the vertical motion. G, all that. Can you fill in some blanks there for me? So what do we get? We have negative. Yeah, negative 1/2 g, but in this case we'll use, since everything is in feet, we'll use 32 feet per second squared times t squared. Keep going, anyone? Plus, what's the initial velocity in the y direction? Yeah, it's 30. Now, some people might be saying, well, wait, doesn't it say 30, isn't it 30 times the sine of the angle? Okay, well, yes. What's the sine, what's the angle here, though? 90 degrees. Sine of 90 degrees is 1. So, we're not lying here. In fact, we could, off to the side, just say, what is the velocity vector that we're even talking about here as we launch the ball? Well, it's nothing in the in the x direction. And it's all of it, 30 in the y direction, upward, right? So that would be like, if you wanted to, you don't need to write that down, but you know, that would be your initial velocity vector if you're trying to come up with like what the initial velocity was. Plus something else then. Looks like the height of the hand as it left there was 75. So did we come up with some parametric models? I think we did. Does that really capture the movement of this ball? Time to get your calculator out if you haven't already. And if you've got your calculator in its normal kind of mode here, I'd like you to hit mode and then follow along button by button here. Go to parametric mode instead of function mode. Did you know your calculator could even do that? So exciting. Okay, so change your mode to parametric. And then when you go to y equals, you'll see something which is actually kind of makes sense in terms of what you would expect here. Instead of y1, y2, you have x1, y1, x2, y2, right? Which makes sense because you know that for this, we're going to need to put in 2 equations. And notice when you push your xt theta n button, you'll just get t. Right? So what do we say? 8 is what we decided on? Okay. And then negative 16 t squared plus 30 t plus 75. And now don't go too crazy. Don't hit graph yet. Let's go over to the window. Let's go over to window. And we're going to go, how about for 0 to 4 seconds? Notice that here we have control. Let's do 0.01 for the t step. Notice that in your window you have more than just x control over x and y now. They're min and max and all that. You also have control over t as well. Let's make the x min and max something that captures 8, I guess. I'll make it 0 and 10 is fine, whatever, okay. Y needs to capture all the different height values we might get for this ball. So 0 would be the ground. I think I'm happy with that. The Y max needs to be something bigger than 10, though. I mean, for goodness sake, it leaves the hand at 75. Y equals 75. So, and then it goes upward. I haven't actually calculated the max, but I don't know, maybe 100? You want to call it 100? You could, just to be safe, make it 120 if you want. I don't know. And then we can always redraft it if it's not right, but I don't know how high this kid's going to be throwing the ball. All right, and then one other thing. Let's go over to y equals again and change this right here. And even if you have an older calculator, you can do this. You don't need to change the color. But change this to the ball. On an old calculator, you just go over here and press enter a couple times until you get the ball. All right, now are you ready for the cinematic experience? Here it comes. Are you ready?
Wait, does it just say 0?
It's a ball, okay? It's a ball. All right, are you ready for the cinematic experience?
Yes.
Thank you. Here we go.
It just went up and down. Do you remember
What? It's like a real.
It's like a real ball. Let's watch it again.
Oh my god.
All right. So let's just keep in mind before we watch it again, what did you expect to have happen on this video we just watched? We want to. Okay, you put in something very slow, maybe. Okay, that's cool. The T step. If you want to make it go really fast, you can make that T step be something faster. I had it plotting values every 0.01 is what I had. But you can make it 0.1 and it'll go a little faster. Yeah, so just keep in mind, what are we expecting to have happen? At all times, we expect the x coordinate that's plotted to be 8, and we expect the y coordinate to be 75 when t is 0, and then something higher than that. Slowing down, and then as it comes down, speeding up in the way that Aiden and I were talking about, getting faster and faster as it goes toward the ground. So just watch it again. Always the same x value, and then faster and faster and faster, boom, right? Okay. All right, let's move on to the next problem here. This time we're dropping a piano from the roof.
How do we do piano on the calculator?
There is no piano button, unfortunately.
That was on the recording. I'm going to go down and just...
All right. All right, there we go. There's our piano. Drop that piano. So we can start doing this. We can say it sounds like a similar situation. We've got x of t equals favorite number. Someone? What did you say? 6. All right. 0 I hesitate to do because I don't want it going up and down on the axis because I won't be able to see it real well. Sure, you can make it negative. Yeah. No, I'm with you, but I'm just saying our view will be obscured by the y-axis on the calculator. All right, that wasn't very interesting. What's y going to be? Have you learned anything from the last slide? Let's hear it. It'll be negative.
1/2.
It'll be negative 16t squared again. Because we're working with feet still. Plus, what's the initial velocity?
Wait 1 second.
Yeah, it is actually given in the problem right here, right? You don't throw a piano. So you just drop it, okay?
Wait, so what's the velocity?
So the initial velocity is 0 in both the x and y direction. But that doesn't mean it doesn't go into motion. So 0t, or if you want to just omit it, you can. And then plus, we do have an initial height. So I feel like this is pretty good. There's one thing that isn't used in the problem, though, that we seem like we have there. Yeah, so we need to maybe tweak these equations to incorporate the weight somehow. How would that come into play? Help me out here.
bowling ball.
Yes, we need some Galileo people in the room here, right? It turns out the weight is a red herring here. It doesn't matter. So what's the thought here? What's the experiment that Galileo did?
Like, so he supposedly went to the Leaning Tower of Pisa and then like
Yes, it may just be lore, but say it again. Go ahead.
he like dropped two things. I don't
It's
remember
a bowling
exactly.
ball and an apple or something.
No, bowling ball.
Yeah, maybe two. The point is two similar shaped weights that had the same kind of shape, but different weights.
Like not counting errors.
Yeah, and they fell and hit the ground at the same time.
Did you like run down the
That's
stairs?
science. Yeah.
Hey,
God,
don't be
they're
rude to him.
they're like 10
He's smarter
tries.
than all
It
of
is
us.
hard. It is hard for us
He's
to
a freshman
believe.
too.
It is hard for us to believe with our. Thanks. It is hard for us to believe in our human experience that would be the case. Really? You drop a bowling ball and a feather, that they'll fall at the same rate. But it is certainly true that that does work if you're in a vacuum, right? I don't know if you've seen that happen, but we'll have to maybe we pull up a video of it. It is really amazing to see that happen. If you've never seen it happen, it's worth watching. In a vacuum, a feather really does drop like a rock.
Face down.
Yeah.
When there's no, when you're not throwing it up, with a component form, just be 0, 0.
Yeah. If you're looking for like the initial velocity vector here, it's 0, 0. Yeah. It's not maybe worth mentioning, but there it is. This is just free fall. This is free fall, right? All right. Next question. It does ask some other questions here. When will it hit the ground? What are we asking there? We're asking when what? When y is 0. So tell me when it hits the ground. When does it hit the ground?
Oh, wow.
100 over 16. Take the square root. 10 fourths by 2.5. 2.5. 2.5 seconds is exactly when I guess it hits the ground. And what's the other question? How high will it be after 1 second? That's us plugging 1 into our y equation. And that gives you what? How about 84 feet, right? Okay. So those are equal,
Okay.
right? I mean, I didn't make any estimates there. Yeah, those are exact answers, not rounded. Good. All right, let's talk about runner A and runner B now. We'll capture the flag. So we got the scene here, and I'd like to propose that we put the y-axis right here. Okay? And we have runner A coming from 50 feet over here and runner B coming from 50 feet over there, and I'd like to set up two sets of parametric equations. I say x of A, x, we'll call this one XA and YA. And we'll call for runner B, we'll call these equations XB and YB, and we'll watch them run two separate motions that'll be modeled here. Well, I just made those. I think that's a good naming convention, though. Now this time, the reason we go to this example here is because we have motion only in which direction now?
It's on the
Yeah, and not in the y direction. So again, this time we'll pick your favorite number.
7 now.
I'll do these at 3, okay. And that will be, we'll set our y value to be that, okay? And both of them will get that same, so they're running on the same y line here. So at all times, the coordinate of the y coordinate will be 3 for these runners, at all times. Soon, on the next example, we're going to have x and y both be interesting equations, I promise, okay? But for now, we'll do this. All right, and then if this is the y-axis, then the initial position of runner A is negative 50. But we want it to be true that every 9 seconds, every second, this runner moves 9 feet to the right. Yeah. So how do we get that to happen? At 3 seconds, let's say, how would you figure out where this runner is? You take negative 50 and then add what to it? Yeah, add 27 to it, which is 9 times 3. So in general, if you want to know where you are t seconds later, you take negative 50 and add 9t, right? It's just this kind of linear movement, yes? Just verify by plugging in t equals 0, 1, 2, 3, that this is doing what you want it to do for runner A. Yes? Let's try it. Is it working? All right, and then for runner B, we'll do something similar, right? We got 50 And then let's ignore the hesitates for 0.1 seconds part for now. How do we deal with the running 10 feet per second? Can you use my idea here? Yeah, okay, good. Minus 10t. So don't forget about the hesitation for a second here. Does that seem to be doing what we want, though, if there weren't no hesitation? We start at 50. If t is 0, we're at 50. If t is 1, we're at 40. Okay, yeah, makes sense. So how do we now accommodate the 0.1 second delay? Can we think of, can we adjust this equation so that when we're at 0.1 seconds, we're actually at position 50? How can we quickly adjust this equation, Bryn? Yeah, well, minus, in this case, 0.1, right? Now verify that that actually does the job of with including the hesitation, right? If you plug in 0.1, are we at 50 then? Yes. And if we plug in 1.1, that's a second later after we're at 50, are we at 40, etc.? It does seem like it's working. Good. So in a minute we'll figure out which runner wins. Let's pull up the calculator again. This is exciting. We're going to watch this competition happen. I'm going to put in, what do we say, negative 50 plus 9t. And here we're just putting in 3. Down here we're going to put in 50 minus 10 times t minus 0.1. Put 3 here. For the red guy here, we're also going to get the ball. There we go. We need to mess with the window a little bit too. Let's go to 6 seconds just because I've done this problem before. Let's do 0.1. 0.1? It might be too fast. I don't know. Let's see here. X needs to, I think, maybe go from negative to positive 50 if you think that would make sense based on how we set things up. And Y should just be something such that we get catch 3. Is that what we said? Yeah, so 5, sure, yeah. All right, and then one other thing you need to do, go to mode. Are you following along? And instead of sequential, this is for the cinematic experience, friends. Go to simul. What does that do, you think? Simultaneously graph the equation instead of one after the other. Okay? All right, are you ready? If you're over here, you're cheering for runner A. If you're over here, you're cheering for runner B. Okay, are you ready? Here we go.
Go runner A.
Oh, that was so fast. Yeah, runner B. Here, let's slow it down just a little bit. All right, pretend like you didn't see who won. All right, here we go. Ready? Come on, runner A. Or come on, runner A. Runner B.
Wait, are we B? Wait, what?
It did.
I root for who I want.
It did appear that runner B won. But can we put a slightly? And that was very exciting. I think we'll all admit. Is there a more technical way of getting that though? From now, I mean, watching it was fun, but that's not quite precise. Yeah, definitely. Yeah, find out when this runner is at position 0 for X, right? So figure out what that is, and over here, figure out when runner B hits an X value of 0. So solve there, the both of those here. So here we get 50 over 9, which is approximately 5 and change, 5.5 ninths. Yeah, so 5.56 seconds about. And over here we get exactly 5.1. If you plug 5.1 in, right, you get 0. 5.1 seconds. So is it clear now from this too that runner B is our winner? Okay, and then the other question is how far away is the other runner? So how would we ask that? In the moment that runner B wins, where is runner A? Yeah, so we need to evaluate where is runner A, X of A, of 5, if we want to answer that question. And where are they? Plug it in. What is it? We plug 5 in here.
I think I actually understand.
Oh, 5.1, sorry. So what does that come out to be?
Oh,
4.1, I hear you say, or negative 4.1. Yeah, so this is a this race really is nip and tuck. The moment B hits the flag, runner A is only 4.1 feet away. That's heartbreaking. All right, we gotta quickly 4.1 feet is the answer to the second piece there. All right, we're gonna quickly do the last question. Make sure we say what we need to say here. So on the last question, we finally have velocity happening in both directions. Ashley hits a baseball 4 feet above the ground with velocity 120 feet per second at 35 degrees. So right away, if you want, we don't have to write this down, but I'll write it down just to make sure you understand, right? The velocity in the x direction and the y direction are both non-zero. In the x direction, it's 125 cosine 35. And in the y direction, it's 125 sine 35. So here we go. Let's write down our equations. X of t equals and y of t equals. And we'll just obey those equations that you have there in the box or whatever. So in the x direction, it's 125 cosine 35 times t. It's just linear, right? Plus 0 if you want. I mean, you can just put the y-axis where the ball being hit is. And the y direction, we're working in feet again. Okay, so it's negative 16 t squared plus the same kind of thing for y now, right? 125 sine 35 times t plus, what's the initial height of the ball? 4. All right, so this set of equations, and I'll let you graph that in your own time. You can see it when you watch it. Of course, it looks like a parabola. It's not that exciting. You can make it a ball, though, and maybe it'll be exciting. I don't know. That will model this situation. The next question says, will the ball clear a 25-foot wall that's 400 feet away? So how do we analyze that, though? It's an interesting question. My first question would be, when is the x-coordinate 400? Do you see that? I don't know if that will help us, but I do know that that will be an easy question to answer. Do you see that we could easily answer when will the x-coordinate of the ball be 400? So we'll figure out what that is if someone has a calculator. And then what will we do once we know that? That is the time at which the x-coordinate is 400. What would we next like to know? Yeah, plug it in to whatever we get there. Plug that time into the y equation and see if you get a y value. What's the critical thing we're going to ask? Does the y coordinate at that time, is it bigger or smaller than 25? This is going to be the big question. So what do we get here for t? Make sure your calculator's in degree mode. 3.9. Now, I would recommend storing this value or using your answer feature or whatever, right? Don't actually plug in 3.91, but whatever. And then, so now in the second equation, very carefully plug in your value that you just got and see how high the ball is. Let's see if we can get this before it goes. How high do you get for the ball? At the time when its x coordinate is 400, at that time, what is its y coordinate? Did you get the same thing back there? Okay, 39.9, the results are in. Did Ashley clear the fence, the wall, whatever it is? Yes, by a long shot, by almost 15 feet, right? So there are lots of more questions that someone could ask in these situations. This wall question is such an interesting one, or the race question where we're asking how far away are they? Okay, now what time are they? Who wins? All these kind of questions we can ask, which require a little bit of an understanding of like what your models are actually doing. Whew. Okay, so homework, I think you're pretty well prepared for homework 6 tonight. Thanks for your attention, and have fun playing around with parametric mode too on your calculator. You can have more.
I'm gonna have
you can have more fun with the ball and all that.